All right, so in the last lesson, you learned how to draw Lewis dot diagrams. And now we're going to go even further into investigating the shapes of these molecules and then also their bond angles. All right, so there are a couple of terms that we need to go over. The first is the difference between the electron group geometry, also known as the electron domain geometry, and then the shape or the geometry in general, the molecular geometry. So let me show you that difference. The first concept we need to go over is this concept of electron groups. All right, so electron groups tell you how many bonding and how many non-bonding electron domains you have, or how many bonded atoms and how many lone pairs you have. Okay, so we can either call bonded atoms, I'll often refer to it as bonding domains. And for lone pairs, I'll either call it lone pairs or non-bonding domains. All right, so the number of total electron groups, or the total number of electron domains, is the sum of your bonding and non-bonding domains. So for example here, in CO2, when you draw CO2, the Lewis structure for that, you've got simply two double bonds. So you've got two bonding domains and no non-bonding domains, or two bonded atoms and no lone pairs. Okay? The shape of this, it is linear, and the bond angle, since it's just a line, is 180. All right, not too crazy. For the next one, if you look at H2CO, for example, H2CO has a double bond with oxygen and then a single bond with the two hydrogens. Okay, so notice it has three bonding domains, 1, 2, 3, and no non-bonding domains or no lone pairs of electrons on that central atom. Okay, so even though they're lone pairs of electrons on the oxygen, we're focusing solely on the central atom. So there are three bonded atoms, okay, which means that the electron group geometry is going to be trigonal planar. All right, and the bond angle is 120. If you look at SO2, however, SO2, the Lewis structure, has a double bond with oxygen, single bond with oxygen, and then a lone pair here. So here's where we get into the concept of the shape or the molecular geometry. Notice up until now, the electron geometry and the shape have been the same, and that's because you don't have any lone pairs of electrons on your central atom. So the shape here, the electron group geometry is linear, the shape is linear. The electron group geometry is trigonal planar, the shape is trigonal planar. Here, however, is where it gets different and we need to talk about it. Since I have two bonded atoms and one pair of lone electrons, or one non-bonding domain, I have a total of 3 electron groups. Therefore, my electron group geometry is going to be trigonal planar, 3. Right? I've got a total of 3 electron groups, 2 bonding, 1 lone pair, or 1 non-bonding. Okay? However, since I have that one non-bonding, this isn't an atom, this is a lone pair, the actual geometry of this will look very different than the one above, right? This has 3 things coming off of this, this only has 2. And so the shape of this is going to simply be bent, which begs the question, why the heck do we call this trigonal planar to begin with? Well, the reason is in determining what our bond angle is going to be. Because it has 3 total electron groups, its bond angle is going to be very close to 120, just like its parent molecule. The one thing I need you guys to change in your notes, however, is that the bond angle is not exactly 120. Because it has a lone pair of electrons here that are going to be pushing the atom downwards, the bond angle is actually going to be less than 120. It's close to 120, but it's less than it because those lone pairs of that lone pair of electrons is going to repel the atoms downwards. All right, let's look at this even further with the last 3 examples. All right, if, for example, you have CH4, right? I've got 4 bonding domains or 4 bonded atoms, Okay, they're all hydrogens. Since I've got 4 of them, the electron group geometry is going to be tetrahedral. And since I don't have any lone pairs of electrons on my central atom, the molecular geometry will also be tetrahedral. Okay? The bond angle here will be 109, or I will often refer to it as 109.5. Okay? And that is using your VSEPR model, making sure that the atoms are as far apart from one another as possible. If you look at the next example, NH3, however, NH3 has 3 bonded atoms, or 3 bonding domains, and 1 non-bonding domain, or 1 lone pair of electrons. All right, so it still has a total of 4 electron groups, or 4 electron domains, but 3 of them are bonding and 1 of them is non-bonding. All right, which means its molecular geometry is going to be different than its electron domain geometry or electron group geometry. Okay, it's going to be trigonal pyramidal. It creates what looks like a little pyramid here. All right, and again, the reason why we care about the electron domain geometry is because that dictates what our bond angle will be. So since it has that 1 lone pair of electrons, which will repel the hydrogens further downwards than the hydrogen would, the bond angle is going to be less than 109 or less than 109.5 if we're being exact. Okay, let's look at one last example here. H2O. When you have H2O, you've got oxygen with 2 hydrogens and 2 lone pairs of electrons. So I have a total of 1, 2, 3, 4 electron domains or electron groups. Okay, that means that the electron domain geometry or electron group geometry is going to be tetrahedral. I have 2 bonded atoms and 2 lone pairs, right? 2 bonding, 2 non-bonding domains, which means that the molecular geometry is not going to be tetrahedral. It will in fact be bent, just like this one up here. But these 2 bent shapes have different angles, and that's because this has an electron domain geometry of tetrahedral, which means its bond angle will be less than 109.5 or less than 109. If I needed to compare this bond angle and this bond angle, since this one has 2 lone pairs, its bond angle is going to be much less than 109.5. Well, this one will be much closer to 109.5. All right, so let's look at 2 quick examples here. So it wants us to draw the Lewis dot diagram for the following molecules, and then identify the electron group geometry and the shape of the molecule. It also wants me to identify the bond angle. All right, so for PBr3, I'm going to count the total number of valence electrons. Phosphorus has 5, bromine has 7, but there are 3 bromines. So that's going to be a total of 26 once you add them together. So when you draw this, and I've gotten to the point where I'm comfortable knowing that I'm going to have it look like this. If you need to draw it out and then realize that there's going to be a lone pair of electrons on phosphorus, and then redraw it using your VSEPR model, that is totally fine. Okay, but this is going to be my Lewis structure. I recount, and I'm using 26 valence electrons. All right, so I'm good there. So if you count, I have 1, 2, 3, 4 total electron domains or electron groups, which means the electron group geometry is going to be tetrahedral. All right. However, since I do have 1 non-bonding domain or 1 electron pair here, my molecular shape, okay, is not going to be tetrahedral. It will be trigonal pyramidal. Okay, and then finally it wants to know the bond angle. So since this electron group geometry was tetrahedral, my bond angle will be close to 109.5. However, since I have this lone pair of electrons here, it's going to be less than 109.5. Okay, let's look at the next example, O3. So if I have O3, I've got a total of 6 times 3 valence electrons, 18 valence electrons. This is kind of a weird one because it brings up the question, what's my central atom? Well, they're all oxygen, so it doesn't really matter. Okay, I have no idea what this is going to look like, so let's draw it out. I'm sharing lone pairs of electrons, 2, 4, 6, 2, 4, 6, 2, 4, 6. Okay, so I'm now using 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I'm using too many electrons. So as soon as I recognize that fact, that means I need to use a double bond. All right, so then I'm going to use my eraser. I'm going to get rid of that lone pair. So it's 2, 4, 6, 8 on that oxygen, 2, 4, 6, 8 on that oxygen. And now I need to make sure I have the correct Vesper model. So use the simulation, and you're going to be using the simulation, you're going to be creating a molecule that has a double bond, a single bond, and a lone pair. So this is what it looks like. Keep in mind, since I've got just one double bond, this is going to be a case of resonance. So yes, you even have to draw it even when I'm just asking about the shape. So it's going to be an average of a double bond and a single bond is what's going to exist for O3, which by the way is ozone. Okay, so what is the average of 2 and 1? 1.5. But our best way of drawing 1.5 is just like this. Okay, so now for the electron group geometry, I've got 1, 2, 3 total electron domains, which means that my electron group geometry is going to be trigonal planar. However, since I have a lone pair of electrons here, a non-bonding domain, this is going to cause the molecular shape to be bent. But since the electron group geometry was trigonal planar, my bond angle will be close to 120, but because of this lone pair of electrons, it's going to be a little bit less than 120 degrees.
Next concept, and this is key because we're going to be using this when we're talking about why molecules exist the way that they do. Polar versus nonpolar. Okay? Polarity for molecules, atoms will pull electrons with different forces depending on their size. That concept is electronegativity. I'm not going to get into that in detail in this class. What you need to know is simply that two different atoms will pull electrons with different amounts of force. And so as a result, if you notice here, what is created is what we call a dipole. So notice oxygen is pulling electrons towards it. This oxygen is pulling electrons towards it. Those arrows are called your dipoles. Okay? And if those dipoles cancel, meaning if you imagine a tug of war, an oxygen is pulling on carbon, and this oxygen is pulling on carbon, that carbon wouldn't go anywhere. It would stay put. Its dipoles cancel. In that case, your molecule is nonpolar. And let's look at another example. Here, I've got carbon in the center, and I've got a chlorine pulling it up that way, another chlorine pulling down, pulling down, pulling down. Imagine you have 4 different people pulling in all of these different directions, and you're just standing there right there. In that tug of war, you would not move. And so as a result, what we say, we don't say, oh, in a tug of war. We don't use that terminology. We can think of it that way. But our way of explaining it scientifically is to say that the dipoles cancel. Okay? Meanwhile, if your dipoles do not cancel, then your molecule is going to be polar. So one example is with HCl. Notice chlorine is pulling the electrons towards it. Nothing is you don't have something counteracting pulling backwards at all. And so nothing is canceling that dipole. And so as a result, we say that the molecule is polar.